Hello everyone, how are you people? So I am over here back again with this very new episode of our crash course, and the topic is gravitation. But first tell me how many of you are waiting, how many of you are there in the chat list, and just tell me, am I audible to all of you? Am I audible? Just tell me, just let me know, am I audible to each and every one of you? Hello, hello Swapna, hello, yes sir, okay. Am I visible to everyone? I am not visible. Just wait for a while. There must be some technical glitch over here. Just wait for a while. It will be starting in a moment, okay? Yeah, so we are back again. Sorry for the trouble. There was a technical glitch, and okay, so now we are here again starting this new session of our crash course, and the chapter's name is Gravitation. Very nice chapter, very brilliant chapter. The weekend is here. You have plenty of time at your home, so just attend the next 2 hours, and I'm sure you will have so many doubts of yours being cleared in gravitation. So many people are here. Good morning, Swapna. Good morning, Edu. I am visible now. Okay. And Joel is saying, sir, can you use at least 75% English because I don't understand Hindi. Joel, there's a good news for you. We have been receiving so many requests from your end, so many people of yours that kindly take the lectures in English. So here we are basically, and we'll be considering your request to us, and the entire lectures can now be attended, and they'll be completely in English. Okay, there will be a pinch of English version in it, but we'll try our best. Your individual physics, chemistry and maths faculties have decided that we'll be taking the entire lecture in English only. Okay, good morning Devendra. Okay, now so let's start the session. You all must be knowing about this crash course session, which is happening daily live at 5 p.m. except for Saturdays when it is occurring at 11 p.m. Okay, sorry, 11 a.m. And now, if I talk about myself, my name is Adarsh Rai. I'm a graduate from NIT Bhopal. I have a very rich experience of 6 years, and in those 6 years, I have mentored so many students who have secured very good ranks in JEE. Okay, they have cleared JEE Main as well as cleared JEE Advanced as well. So many of my students are presently studying, and they have graduated as well from so many IITs. If I talk about Extramarks, you know it very well. We have a very good track record of making students secure a good rank in JEE Main and Advanced. Okay, if I talk about our figure, then out of every 7 candidates, 1 has been selected in JEE, and that is actually a very good record. And we don't say that it is our best. We'll be definitely working on to make it much better than that. Okay, and this figure next year, I'm sure if you are watching it the next year as well, this figure definitely will be 2, 3 or 4. Okay. Then if I talk about the content, the app basically, if you go in the description, you'll find the link to our app, Extramarks Learning app, which you can download it right away. It is on both platforms, and you will get quality content, okay, and that content is basically designed and curated by experts who already have qualified this exam, who are basically IITians and NITians, and they have segmented all those chapters, those units, those subtopics, all those questions in a very segmented profile. So you can just go over there according to your need. You can practice as many questions as you can, and after that practicing questions you can also give test as well. So you also have the availability of giving tests, so that's a very good feature. Even I'll tell you, you can create your own test as well. So during the lecture I'll be just telling you what all features you can do. And let's move ahead, and this is the app, this is the interface of the app. I'll be just telling you about the interface as well during the lecture in between it. So if you have any doubt about the app, about the usage of it, do ping me up on the live chat. I'll be telling you how to do it. And this is basically the app. We are on App Store as well as Google Play Store as well. Now let's move ahead and talk about gravitation. A very beautiful chapter basically. So it's all about those huge galactic bodies, right? And we are a part of it. Although we do never ever try and understand that, because they are on such a grand scale, and when we compare size, so we are just negligible, right, in terms of their huge galactic bodies, but they are definitely creating a change in your day-to-day life. Even now, if you just drop your pen, it will fall down, and the reason is this universal law of gravitation. So this universal law of gravitation is evident everywhere, and this was given by Newton, but it has been modified further by Einstein, and the new theory is about space-time graph, or space-time what to say, there is a curvature in space-time because of which this gravitation is occurring. But on a normal scale, why we are studying this, because this has been not the real model which is present right now. This is not being accepted, but most of our cases, most of our examples can be solved, can be understood using these concepts of gravitation which we will be discussing, okay. But the modern day concept is always about curvature, that space-time has been curved because of gravity, okay. It's about time dilation and so many other things which you will definitely get to know, but only when your base is strong, that is, this unit of gravitation is strong. So this is the reason why these chapters are not omitted from your syllabus, and it becomes very important while understanding these real things, okay. So now let's talk about gravitation. So the first thing is universal law of gravitation. First of all, this is a first fundamental force, the weakest one, but a fundamental force, gravitational force, and it occurs in a fashion with sync to this universal law of gravitation, which instead says that when two masses are placed and there is a separation of r between them, then they always attract each other. Okay, I am again repeating myself. Two masses placed at a distance r, they will definitely attract each other, and this force of attraction between both the masses will be directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Okay, the square of the distance between them, and this is the reason why such kind of forces known as inverse square law, considering or basically following inverse square law. Okay, these forces follow inverse square law, and this is what that means is that F is inversely proportional to r square. Now just eliminating the proportionality sign, we have to put in a constant, and here is this constant G. Okay, so G is that constant, and the value of G is very evident. It's 6.67 into 10 raised to the power minus 11 Newton meter square per kg square. And I'm sure all of you must be able to determine its dimension. It's pretty simple, right? You just need to put the dimension of Newton, of meter, of kg, and you'll finally get to this result. So it's not much of a concern to us. The main concern is to remember this formula. It's very, very important. Okay. So I'm sure all of you must have studied here. Gravitation has been a base in all our studies from 8th, 9th, 10th. We have studied it so many times, so it's not a new thing. The new thing over here will be the vector form of universal law of gravitation. Okay, so how to determine the vector form? So it's pretty simple. Just have a reference vector of r. So this is the position vector of r. Now what this position vector is basically, I have placed my reference point. Okay, for having any position vector, we need to first have a reference point, right, from where we are marking a point. So this is our reference point, and with respect to this reference point, I have located M2, and what I am saying is M2 has a position of r vector from this reference point. So M2 की जो position है, that is represented by r vector. Okay, no problem, no problem. Now I told you all it will be a attractive force. So basically over here the force will be on M1 and over here the force will be on M2. Okay. So M2 पे जो force लगेगा that will be determined by force on 2 with respect to 1 and M1 पे जो force लगेगा that will be given by force on 1 with respect to 2. Okay. So this is what force on mass 1 with respect to 2 because of 2, not with respect to, because of 2. So because of the gravitational field of M2, M1 will experience a force in this direction and that has been the magnitude you very well know, but we need to place a vector sign in it, right? So what I'll be doing, I'll be multiplying a r over here in the denominator, the magnitude part, and in the numerator part I'll be multiplying a vector only. So r vector gets multiplied. Basically this is happening like this. Force on particle 2 or mass 1 because of mass 2 will be equal to, the magnitude is g m1 m2 upon r square. This we very well know, right? This we very well know. Now what we need to do, we just need to multiply a vector with its magnitude. Okay. So why I am multiplying this vector? Because as you can see, the direction of r vector is in the direction of this force. This one is what? F12 force, and this one is what? F21 force. So F12 will be equal to this r magnitude multiplies over here. So finally you get this result, F12 will be equal to gm1 m2 upon r cube into r vector. Okay, there is one more representation of it. You can also write it in this fashion. F12 vector will be equal to gm1 m2 divided by r square into r cap. That is the unit vector along this r vector. This is the unit vector along this r vector. Okay, so this is also representation. This is nothing, this is r vector upon r vector's magnitude. So this can be written in such a manner. Now what about F21, or the force experienced by second mass, that is m2, because of m1? So the force magnitude remains same, right? It will be equal to gm1 m2 upon r square, but the direction is opposite to this r vector. So what I just need to do, I just need to place a minus sign over here. So minus sign over here, minus sign over here will instead turn this F12 to F21. So I suppose you all must have got what I mean to say, that this is how we represent the universal law of gravitation vectorically. Okay, now let's move ahead and talk about some very important points. These points are very important because they are not discussed very nicely and people just omit these points and remember this entire stuff. So the important points are that this universal law of gravitation is applicable only and only for point masses. So you all must be remembering that we have, sir, discussed about the gravitational field and gravitational force between spheres, between cylinders, between different type of objects. So how was that done? That was also done using calculus, but considering universal law of gravitation on small discrete particles, and those discrete particles were dm masses. Okay, so this thing should be very, very important, very, very clear in your mind, that universal law of gravitation is applicable only for point masses, okay, or spherically symmetric masses, obviously, because if there isn't symmetry, then calculus cannot help us in determining the exact value of the magnitude. So obviously symmetry should be there, but this point is very important, that it is applicable only for point masses, and for the symmetrical part we can use calculus and break down that symmetrical part into small point masses and finally integrate it to get our final result. Okay, next point is the gravitational force is conservative in nature. Very, very important point. So if you remember this lecture of work power energy, if you all must have not watched, then you all must see our crash course on work power energy. There I have very nicely discussed about what conservative and non-conservative forces actually are. So gravitational force is a conservative force, and hence the work done by gravitational force will cause a change in potential energy, and the reason is because those conservative forces, when they work, a type of a hidden energy gets stored in the masses in the field of the object and over here in gravitational field, and hence the increase and decrement in potential energy is observed. So this thing should be pretty clear, that gravitational forces are conservative in nature. Okay, gravitational force is always attractive and central. Yes, yes, they are always attractive in nature. They can never be repulsive because we only are surrounded by matter. Okay, and if there exists an antimatter, as in the case of proton and electron, or positive or negative charges, they are just opposite to each other, right? So there is no opposite thing to matter. There is obviously antimatter, but antimatter is not in existence in that amount in our world. Definitely we have detected antimatters, but on a very small scale, okay, on a very small scale, and we'll be discussing about antimatter when we'll be talking nuclei chapter of 12th. There I'll be stressing upon what antimatter is, but for the time being we normally never observe such huge galactic antimatter bodies over here, okay, in the universe. So all we are surrounded is with matter, or you can just clear your mind with this concept that we are surrounded with only positive charge, right? Or not positive charge, but positive and negative charge such that they are only attractive. So matter is only there and the forces exerting on all those matters are always attractive in nature. Matlab, they just get pulled towards each other only. They can never push each other apart. The next point is the gravitational force between 2 points is not altered by other objects. So there's a gravitational force, right? There's a gravitational force, and it cannot be altered by any other. If you place any other force or any other object also in between two masses, then the gravitational force between, say suppose it is m1, it is m2, and m2 is exerting a force over here, ff. Now if you place a mass like this, so this force will remain as it is. Now this will also exert a force in such a direction, and the actual force on m1 will be a net result of both these forces. So this force never gets disturbed by the presence of any object, any material, okay. This force remains as it is, okay. Eddie, you are asking DM masses. DM masses are basically those small elements, right? When we create a rigid body and suppose from a reference point we want to measure the entire mass. We have discussed it in center of mass, right? The previous lecture, the system of particles and rotational motion first part. So we have discussed about DM masses, right? Small DM elements which we use, which we segregate just to infuse calculus and get a final good result over here. So these are some important points. Always keep them in mind, because you can expect so many questions which are not calculative in nature, but just to check your skills whether you have a good understanding about these mere small concepts or not, okay. Now let's move ahead and talk about acceleration due to gravity, a very important topic indeed, because it has been noticed by us that so many questions are asked from acceleration due to gravity, and what all factors actually cause a change in acceleration due to gravity. So first let's just understand what is acceleration due to gravity. And yes, it is obvious that if I drop a pen from this point, it will definitely fall down, and the rate of change in its velocity will obviously be equal to 9.8 meter per second square. Clear? Yes, it's clear. And we have been solving questions based on that, but the reason to this is gravitational force exerted between this pen and earth. Okay, and the reason to this is, let's just understand it, the magnitude of it, using universal law of gravitation. So what happens is, consider this small mass m, and the mass of this earth, this is earth, so its mass is me. Not an issue, okay. Now let's say there will definitely be a force of attraction between this huge mass of earth and the small mass m, right? But sir, you told that this is not valid for gravitational force is not valid for point objects. So what I'll be doing, I'll be considering this entire mass concentrated about its center of mass, and here doing that, what I have done is I have considered this entire mass concentrated about its center of mass, and now this entire me is just concentrated about a point, so it can be considered a point mass, but that point mass is very heavy. Obviously it contains a mass of me, capital M with a subscript E, but it is a point object now, right? It is a point object. Using the concepts of center of mass, I have just located this entire mass concentrated about its center. So now the distance between both these masses becomes Re, that is the radius of earth. So now this relation can be understood very well. So the gravitational force acting between earth and the small mass m will be equal to G capital M small m upon Re square. Pretty simple, right? And what will now be the gravitational acceleration? So because of this force obviously on m will be in downward direction, and on this earth will be in upward direction, right? Obviously this force will be in downward direction of small m, and in upward direction on this Earth in upward direction. So because of this force, both will have an acceleration because there is an attraction force between them. So this attraction force will definitely cause an acceleration to them. So that acceleration, how it can be found? So it can be used, or it can be found out using Newton's second law. So just equate it with m into a. Just equate it with m into a. So if I talk about this mass m, so it will have an acceleration equal to this. And if I talk about this earth mass, so it will be equal to me into Earth's acceleration, right? Now what I'll do, on equating it with this m will get cancelled with this m, and finally acceleration will remain g capital M upon re square. And on equating it with mass of Earth into acceleration of Earth, this will get cancelled, and now the value will be g small m upon re square. Now the point to notice over here is that g has a value already in the order of 10 raised to the power minus 11, and radius also has a value 6400 kilometers. That is nothing, 64 into 10 raised to the power 5 meters, and that too in denominator. So finally when it goes to numerator, the force experienced by Earth will be 10 raised to the power minus around 20 something, okay, and that is not a very big force. And the reason is that only that Earth never has a motion because of these unit masses or small masses, or my mass or your mass or this building's mass. Because of those masses, Earth never experiences an acceleration, and it doesn't move, it never moves, okay. But instead when I talk about small m, it will have a significant amount because of the mass of Earth. And on replacing the mass of Earth over here, finally what you will be getting is that this value is turning out to be nearly equal to 9.8 meter per second square. So what is acceleration due to gravity? It is this relation g capital M upon re square, and that will be equal to 9.8 meter per second square when I talk about Earth. Now if I move to any other planet, then what this relation will change? The relation will have two changes only. This m will get replaced by the mass of that planet, and this r will get replaced by the radius of that planet, okay. If I talk about some other planet, some other thing, then just interchange or just replace the masses and radius by the masses and radius of those planets, and what you will be getting, you will be getting the acceleration due to gravity on those planets as well, okay. I suppose you are getting what I mean to say. तो इस तरीके से हम gravitation, acceleration due to gravity निकाल सकते हैं, और बहुत easily हम आंसर भी बता सकते हैं. Even we can compare stuff as well. So the relation that on moon the gravity, the acceleration due to gravity is 1/6 of us on Earth is done by this only. So we found out the mass of moon, we replaced it over here, we replaced the radius over here, and what we got the acceleration due to gravity on moon. So on moon traveling or jumping is pretty easier as compared to that on Earth, okay. So now let's move ahead and talk about variation in G. This is a very good movie, right? I'm not remembering the name. So in that there's a path in Earth, and through that, it's a sci-fi movie. So through that it moves to some other planet, and there, I think it's John Carter or something like that. So there the gravity is not that much, and what he is able to do is he can jump so huge heights. So how heighted we can go for a jump, right? It can be around 2 meter, 2.5 meter, but he was able to jump those very big heights, or he could make a very good projectile motion over there. And the reason to that was only that gravity on that planet, acceleration due to gravity on that planet was very less as compared to Earth. So a normal push on Earth was able to make us move very higher. So now let's talk about this important stuff, and this stuff is actually very important because it has been asked very many times in exams, and it creates a bit of confusion as well, that which formula to use whenever I am talking about acceleration due to gravity at a height h above the surface of Earth. Okay, so here is our Earth, radius re, and now the mass has not been very near to the surface of Earth. It is now situated at an altitude of h from the surface of Earth. So now will the acceleration due to gravity change? Will the acceleration due to gravity change? Yes, it will definitely change. It will definitely change because now h is somewhere comparable to re. Okay, h is somewhere comparable to re. I'm not talking about that if I have a high-rise building of 28-30 floors and I go on the top of it, so will the acceleration due to gravity change? No, it won't. It won't, because the height of that building, a high-rise building, is also not that much. Okay, so the height of Mount Everest is around 10 kilometers or somewhere near to it, smaller than that only. So at that point, a bit variation, basically at that point this formula is used. So I'm talking about 100, 200 kilometers above the surface of Earth, then you will have this formula of acceleration due to gravity. And what will happen over here, you will experience a force, and that will obviously be equal to G capital M small m upon Re plus h whole square, right? And what I just need to do is I just need to equate it with my mass into acceleration due to gravity at height h. This mass m will get cancelled, and as you can see, the g dash, the new g dash or the new acceleration which I am experiencing will be gm upon Re plus h whole square. Okay, and what I can do is I can just multiply r square over here and r square over here. So this gm upon r square will get indeed converted into small g, and this r square can come over here. So finally you will have this relation that g dash is equal to g upon 1 plus h upon Re whole square. Okay, so this becomes your relation when your height is around 100 kilometers, 200 kilometers, because that's a significant amount, right? The Earth's radius is around 6400 kilometers, right? So the Earth radius basically is 6400 kilometers. So if I go a distance or a height of 100, 200 or 500 kilometers, then that occurs a significant amount. It can get added to 6400, it can create a change over here in the denominator. So this is the formula. Now, but we never go to such height. We can also move, we can go at the top of Mount Everest, right? And there we can experience gravity. So that is around 10 kilometers. So 10 kilometers, when I compare it with 6400 kilometers, so it's a very meager amount as compared to 6400 kilometers. So in such cases, what we have done is, we have now expanded this relation using binomial expansion, and this relation has in turn just put this thing in the numerator. So this 2 will get converted to minus 2, and just put this minus 2 over here. Okay, so this will just get go upstairs, so it will become 1 plus h upon Re to the power minus 2. And what happens in such kind of relations, when h upon Re is very less than 1, so this relation is basically about 1 plus x raised to the power n, and if x is very less than 1, and in this case it is obviously, because my h is now not that much, it can be 5, 10, 25, 15 kilometers around, so that is a very lesser amount as compared to 6400 kilometers. So if such a case arises, then this expression can just be written as 1 minus nx, or 1 if it is minus n, then 1 minus nx, if it is plus n, then 1 plus nx. Okay, so this is the approach which I am using over here. So now the g dash turns out to be 1 minus 2h upon Re, but you should be very clear that now h is very less than Re. So keep this in mind. If h is around given to you 1, 10, 5 kilometers, 2 kilometers, 10 kilometers, 20, 25 or 30 kilometers, I am giving you the approach till 30 or 40 as well. If it is within that range, then you can surely use this formula, or else if it is not specified clearly to you that h is very smaller than Re, then never ever use this formula, because the examiner wants to check you on your skills. He'll tend to drive you towards this relation, but instead he is talking about this relation. So always keep this in mind when to use which equation. I suppose you just keep this in mind, and also keep this in mind, but use it very wisely. Only when it is specifically mentioned to you that the height is not that much, it's around 1 kilometer, 2 kilometer, 3 kilometers, then you can surely use this result. Okay, so I suppose you have got what I mean to say. Now if h is equal to Re, so suppose the height at which we are located is instead equal to the radius of Earth, that is 6100 kilometers, then our g dash will turn out to be g by 4 only. So our acceleration due to gravity will be 1 by 4, and this is a normal value. You just have to replace Re over here, you'll get the same result only. Okay, Edu, you are asking which is real? Mass is real. Mass is mass of planet. Mass is m is mass of planet. Yes, m is mass of planet, obviously. So now let's talk about, we have reached a height h above the surface of Earth. Now let's go deeper. Let's go deeper inside Earth, and now we are situated at a depth d. So this thing you can see over here is nothing, it is depth d. Okay, we have reached a depth d below the surface of Earth, and now what will be the acceleration due to gravity? Will it change? Yes, it will. Yes, it will, my friends, it will. And why it will change now is, If you remember the concepts of Gauss law, which you have already studied in electrostatics, and if you haven't, don't worry at all, we'll be studying them when I'll be discussing about electrostats. So for those who already have learned, you people must be knowing that when I talk about a sphere, with charge distributed all over it, so if I reach at a point inside the sphere, right, then the Gaussian surface is actually created like this. And what Gauss law is all about, that the EDA element over here will entirely be because of the inside charges, and we just consider for uniform mass distributions or uniform charge distributions this outer part. This outer part will definitely not create an electric field at any point inside it, right. The reason is that this part, that actually result can be calculated using solid angle concept, that the electric field through this part is actually equivalent to this part, and through this part is actually equivalent to this part. So the net result of electric field gets cancelled, and all in all what I just mean to say is that the outer region creates a null effect in electric field over here, and this concept is only used over here, that the region which you are seeing right here, the outer region, okay, the outer region will not at all exert a force on this small m mass, okay. The only force experienced by the small m mass will be because of this inside sphere masses, okay, the mass which is residing in this radius of x sphere, okay. So we just need to calculate this mass now, okay. The case remains same. Now the case as we studied when we were at the surface of earth, we need to consider it along its center of mass, and you just need to calculate the force of attraction between these 2 point masses. The same case we will be using over here. We will be considering this entire mass which we are seeing concentrated about its center of mass, and now we'll be having 2 point masses separated at a distance x between each other, and we just need to calculate it. The universal law of gravitation will come into action, and we'll be finally in a state to tell what will be the force experienced by this small m mass. And if you people have not got it, don't worry, we will be studying it in electrostats, and then you will be perfectly clear how Gauss law has helped us in such a case in determining which mass will actually exert a force on this small m mass. Okay, so what will be the force? What will be the force now? So the force obviously will be g small m into m dash. Now the entire mass of earth is not exerting a force, so it will be m dash upon, what is the distance? This distance is obviously I can tell it to be x square, right? I can express it in x square. Okay, so x square. Now this m dash, what will be this m dash? So m dash can be represented as I can consider the earth. अच्छा, one more thing is very important for you people. मैंने जितने भी cases लिए ना, what all cases I have considered, the entire earth I have considered to be constituted of uniform density. Okay, so which is not the real case, right? As we go deeper and deeper, the density increases. Okay, as we go deeper and deeper, the core, basically the part of the core which should be in a liquid state, also gets in a solidified state because of that intense pressure. So density obviously increases, but I have negated those effects. I have just considered that the density of earth is uniform across. You all throughout the radius, the density is uniform. So what I can consider is, I can just multiply the rho with this volume of this small sphere. So now rho into 4 by 3 pi x cube will give me this result. Yes sir, definitely. And I can just cut this x right there. So what I'll be doing, I'll be multiplying this r cube over here, r cube or r square, no r square, yes r square I'll be multiplying. So here it will be r square, and over here also it will be r square. And the reason is that now this g capital M, not r square, it will be r cube. I'm sorry, again it will be r cube, just wait for a moment. So the relation was F is equal to g small m, capital M was replaced by rho into 4 by 3 pi x cube, right, and here it was x square. Now what I'll be doing is, I'll be constituting a capital M over here. So what I'll be doing, I'll be multiplying r cube over here, and I'll be multiplying r cube over here. So this x cube, 4 by 3 pi x cube, this x cube will get cancelled by this, okay, and this rho into 4 by 3 pi r cube is instead what? Mass of the entire planet, right? This is r cube, that is radius of earth. So it can be replaced by capital M. So it will be gm I'm writing it over here, F is equal to G small m, this can be replaced by capital M, and now this r cube remains as it is, x divided by r cube. Okay, I suppose you have got. Now this F will be replaced by m into acceleration due to gravity. This m will get cancelled by this. So acceleration due to gravity will be gm upon r cube into x. Now this r cube can be further broken down into r square into r, and this in turn is what? The value of g. So this acceleration due to gravity is instead turning out to be g x by r if I mention it in terms of x. Okay, if I mention it in terms of x. So over here it is not x, basically x will be this distance. Okay, so it will be g x by r, and if I consider this distance to be d, okay, then this x is what? This x is instead re minus x. Okay, so I just need to replace this x by re minus d. So here it will be replaced by re minus d. Okay, I'm again. So the relation turns out to be this: a is equal to g into x by r, where x is this distance. Now what I can do, I can replace it with this distance. This is what? This is d, the depth below the surface of earth which you are going. So this x can be replaced as g into r minus d upon r, which in turn will be 1 minus d by r. So the x which you are seeing over here is not x, it is equal to d. That's what I meant to say. So this d, the depth below the surface of earth which you are going, will have a change in gravity like this, and the actual relation of g dash will be equal to g into 1 minus d by r. Okay, so I suppose you people are clear. If you're not clear, just rewind the video for a while and you will get to know how I got this relation, and finally the relation between the acceleration due to gravity at this point at a depth d below the surface of earth in terms of the real acceleration due to gravity at earth, and obviously it will be lesser, right? It will definitely be lesser. As I go up, then also acceleration due to gravity is lesser. If I go down, then also acceleration due to gravity is lesser. At the center of earth, obviously g dash will be equal to 0 and weight will be equal to 0. So anybody interested in decreasing its weight, just give them that, take your weighing scale and either go on the top of Mount Everest or go below Mariana Trench in Pacific Ocean. So at both those points you are at a great depth and great height, and obviously the acceleration due to gravity will decrease at a significant amount, not a significant amount, but it will definitely decrease, and finally he will get those 5-10 kgs which he is practicing on daily, reduced in a very short span of time. Now let's talk about this due to rotation of earth, and it is very also important because we talked about that how acceleration due to gravity has changed when I go a height h above the surface of earth, d below the surface of earth. Now because of the rotation of earth also, there occurs a decrement in acceleration due to gravity, and I'll tell you the reason why. Okay, so me presently standing over here, you sitting in your house, are we at rest? Are we at rest? This question in itself is incomplete because we aren't. Reason is, if somebody is observing us standing on ground, then he'll surely say that yes sir, you are on rest, and even I am on rest because I'm standing, I'm sleeping, and whatever I'm doing at my house, we are at rest. But a person outside in space or on moon will definitely say, hey bro, you are in rotation continuously, so how can you say that you are at rest? And that's what I mean to say. We are in rotation, we are continuously accelerating, our velocity's direction is continuously changing, and our velocity's direction is continuously changing means that we are in an accelerating frame. We are actually situated in an accelerating frame. So if I am experiencing an acceleration due to gravity, suppose I am located at this point, okay, I am located at this point and I am experiencing an acceleration due to gravity towards the surface, towards the center of earth, and that's pretty obvious. We are situated on the surface of earth, right, and we experience an acceleration due to gravity towards the center of earth. Now what will rotation do to me? There is occurring a rotation like this, right, there is occurring a rotation like this. Now I am standing on an accelerating frame, so I am experiencing a force mg, but I remember that pseudo force concept of inertial non-inertial frames. So me being situated on a non-inertial frame, I cannot, the Newton's law won't be valid on me, right, unless I add a pseudo force element on it if I am observing things from an accelerating frame. and that's what it is. You are in an accelerating frame whose acceleration is obviously towards the center, not towards the axis of rotation. And how much it is? It obviously will be equal to m omega square r, because you are actually rotating in this circular path. You are actually in rotation just because being situated at this point on the surface of Earth, and you are in rotation, you are in a circular orbit, so there obviously will be a force towards your center, and this is that point, so this force is your acceleration and the frame's acceleration in which you are a part of. So definitely on observing things from that frame only, you will have to apply pseudo force opposite to the direction of your frame's acceleration, and this is that force popularly known as centrifugal force. So you will have to apply a centrifugal force over here, and this centrifugal force will have a component like this, mr omega square cos lambda, wherein lambda is this angle, the position, the radius of the radial direction is making with the horizontal, with the equator. So this m omega square r cos lambda will definitely decrease your mg force, and this is what happens, and this is what variation of g is when you are situated on Earth, and because of the rotation of Earth only, your acceleration due to gravity changes, it gets decreased, and this is the reason behind that. So as lambda becomes greater, and as I reach poles, so then lambda is equal to 90 degree, and obviously cos lambda then will be equal to 0. So there will be a null effect because of the rotation of Earth, and this effect will be maximum when I am situated at equator. So keep this in mind. This is the expression how your acceleration due to gravity changes. So how it will change? It will change actually, this is the relation. G dash now will be equal to G minus R omega square cos lambda, wherein lambda is the position of yours with respect to the equator. Now suppose there can be a hypothetical situation asked from you in your exam, that suppose you are on a planet, and now the planet doesn't have a rotational period of 24 hours, it is having a rotational period of 60 minutes or 15 minutes. So then this omega square will be huge, and in such a case obviously this g, it can occur in such a fashion that the net force acting on you is 0. And this can obviously occur if suddenly Earth starts to rotate at a very higher rotational speed, then obviously we without even knowing, we will be just getting uplifted up from our surface, and this can actually occur if Earth's rotational velocity increases drastically. So this can definitely occur. You must have there is a dam made in China, I am not remembering the name, it's a very huge dam, and it actually the dam is so huge, it's the Three Gorges Dam, right? So the dam is made so huge that the accumulation of that volume of water in such a small stretch actually created an impact on the rotation period of Earth, right? And the reason to this was not because of this gravitation and all, the reason to this was conservation of momentum, conservation of angular momentum, basically, that how moment of inertia, they changed the moment of inertia from the axis of rotation, they made a huge galactic mass over here, and suddenly our omega got increased or decreased. There was a slight change in omega, so that was the thing I just wanted to say. So suddenly if our omega, that is the angular rotation of Earth, changes drastically, we can definitely experience a situation where we are rising from that Earth or from our planet. Okay, so these are the three variations. One more thing I want you all to remember is that because of the structure of Earth, so Earth is not exactly spherical in shape. Earth has a shape popularly known as a geoid shape. Okay, the name is geoid, and what that means is that it is flattened at the poles. And curved at the equator, and due to that the radius at poles is very less as compared to the radius at equator. Okay, so the radius at poles is very less as compared to radius of equator, and this is the reason the acceleration due to gravity at poles is very more than the acceleration due to gravity at equator. Okay, so this is also the fourth variation in G. So now I suppose all of you must have got what all variations in G can occur because of the structure, because of the rotation, because of the height, because of the depth of us moving here and there on this planet. Now let's solve this question. It's a very interesting question. If the radius of Earth decreases by 1.5%, okay, so it is decreasing, mass remaining same, then the value of gravitational acceleration G at the surface changes by. So what we need to find? We need to find the acceleration due to gravity, the value of g at the surface, how much it is changing. We very well know the relation here. So g is what? G is gm upon r square. Now is mass changing? No. Is g changing? No. Only r is changing. What we can do is, and the increase, the decrement amount is very small. It's very small, 1.5%. How much it is? Just divided by 100, 0.015. So that's not a very big amount, and I can definitely use those concepts of errors. Those concepts of errors which are actually in turn derived using calculus. So I can use them and I can write a relation like this: delta g by g will be equal to 2 times delta r by r. I suppose you are getting it. So what will be the value of delta g? So delta g by g will be equal to 2 times delta r by r. It will be equal to 2 into 1.5, that is 3. And what we need to do, just multiply it with 100. You'll get the value. This is coming out to be 3%. This is coming out to be 3%, because this 1.5% is instead the not relative error, not delta r by r. It is delta r by r into 100. So initially only we had to multiply this 100. Okay, and this value is what 1.5% is. So delta r by r into 100 is equal to 1.5 into 2, it will be equal to 3%. But the important point is, will it decrease or will it increase? So g is having an inverse relation with r. So if r is getting decreased, then obviously g will increase. So the answer will be plus 3, and it is pretty simple. I suppose you all must have got how this answer came. So it will be plus 3% because r is having an inverse relation with g. Now let's move ahead, solve this. Another very important question. Okay, what should be the angular speed with which Earth has to rotate? Okay, this question is what I was talking about its own axis, so that a person on the equator would weigh 3 by 5 times as much as present. So now the position now is that the person is equated. Okay, one very important thing again, axis, I am actually using that this is our axis of rotation, but it isn't. Our axis of rotation is slightly tilted. It is slightly tilted, and this tilt is very, very important. The seasonal changes, this winter, summers and rainy seasons which we are experiencing right now, winters are experiencing, and this winter season we are experiencing because of the tilt in our axis of rotation. So the actual axis of rotation is like this, but for calculative part I will be using such axis only, because that makes our result very simple. Okay. So what should be the angular speed with which Earth has to rotate about its own axis, so that a person on the equator would weigh 3 by 5 times as much as present? So here is the person, here it is mg force, and this should be its actual weight, right? This should be its actual weight. Now how much amount of centrifugal force it will be experiencing, because situated on equator, it will be equal to m omega square capital R, and capital R is what? Radius of Earth. So this will be the decrement in its force. Now what should be the new force then? So W dash will be equal to W minus m omega square R. Okay, fine, and this W dash should be equal to 3 by 5 times W. Should be equal to 3 by 5 times W. It will go over here, m omega square R will come over here. So m omega square R will be equal to 2 by 5. Omega W minus 3 by 5 times W, it will be equal to 2 by 5 times W, and weight is what? Mg. M will get cancelled. So omega will instead turn out to be, omega is equal to 2 by 5 G by R under root. You can even find the value. You can replace G by 9.8 and R by 6400 kilometers. You will definitely get the value. What should be the omega? And instead you can also find the time period. Then just equate omega by 2 pi by t. You can also tell me what will be the time period of rotation of Earth, such that such kind of a case occurs, that the mass on this planet is somewhat like this. Comment in the chat box. I want to hear the answers. If you have finally got the result, what should be the value of time period? Just calculate the time period and tell me how much time is coming, how much should be the time period of rotation. And if you are loving these sessions, so I need not say, but still I am saying, like these lectures, subscribe and hit the bell icon, because it's very important. You will be getting the updates on a regular basis. Also do call your friends. I am not able to see so many of your friends over here. I actually want those learners, those real needers who need these lectures to be over here. that these lectures are very important, boss. These are very important, and instead you will definitely feel by the end of this crash course your existing preparation is on next level. You have definitely achieved something by just spending 2 hours a day on this YouTube platform. Okay, and then after that obviously practicing yourself and enhancing your skills, but that is your own time which you need to spend, right? But just to listen someone on a platform like JEE platform of Extramarks, just 2 hours of your investment will definitely create a great change by the end of this crash course. I am pretty sure about it. Okay, now let's move ahead. So the answer is right. It is right? Yes, it is right. Now let's move ahead and talk about gravitational potential energy. Okay, so one thing is देखो very important. If you all have studied electrostats, right? अगर आप लोगों को electrostats बहुत अच्छे से आता है ना, gravitation is just like nothing. फिर gravitation में you just need to study 2 or 3 concepts. First one is this variation of G, ठीक है. The next one will be escape velocity, and the next one will be orbital velocity, relation between escape and orbital velocity, and trajectory of motion of satellites. That's all. Because rest all the concepts are just in sync with electrostats. So there are the unboxing of electrostatic force or the Coulomb's law over there is just like the unboxing of universal law of gravitation over here. So as over there Coulomb law, then electric field, then electric potential energy, then electric potential, the same thing happens over here. Universal law of gravitation, then after that gravitational field intensity, then gravitational potential energy, then gravitational potential and whatnot. So it's not wise enough also in this limited time frame to do the questions twice. If you are perfect in gravitational potential energy, then you should be sure that you can actually ace the concepts of electrostats also very nicely. And if you are perfect over there, then these things will obviously not be a trouble to you. The only difference, one more difference lies over here, that over there the constant is 1 by 4 epsilon naught, and over here the the constant is G. Okay. So this is the difference. Rest all the things, obviously Q1 gets changed to M1 and Q2 gets changed to M2, and rest other things remain same. So just learn things creating a similarity, that will definitely help you. Using physics, always study physics like you're feeling it, like you can observe things. So what all things I am telling you, they're not hypothetical, right? You can obviously observe them. You can drop your pen and obviously feel what acceleration due to gravity is. So these things are real, and physics is all about reality. So learning things when they are real, it's a very mind-blowing thing. So you must have also noticed that you learned a concept, you just applied it, and that concept will be remembered by you for the rest of your life. So just try and learn physics by relating it with things, by relating it with different concepts, by creating a mind map, and the mind map is solely yours. You can create it in your own way. Okay. Let's get back over here and talk about gravitational potential energy. So what it is, I'll just tell you the final relation. This is just the derivation part, how we used, this is the conservative force obviously, and delta U will obviously equal to integration of F dot dr. So such a relation will occur, and finally what you need to remember is that between two masses which are situated at a distance r, m1 and m2, so the gravitational potential energy between them of their 2-point system masses will instead be equal to minus G m1 m2 by r. Okay, and r is what? The distance between them. M1 and m2 is obviously the masses. And why, sir, the negative sign? The negative sign is basically because we have considered the case when both these masses, which are placed right now at r distance, when initially they were at infinite distance, the gravitational potential energy was 0. Okay, it was 0. Now it was 0 as they were very far away from each other. Now they are coming close to each other. Okay, and I should tell you one thing, this thing also you should always remember in mind. Things always tend to achieve a stage of stability. Okay, there is a driving force which always compel them to reach their maximum stable state, and this is the reason why the surface and the structures of all the planets and stars are spherical, because I'll be telling you that in surface tension as well, that why the entire construct of our planet, so many planets are always spherical in shape. Why aren't they cubical or cube or cuboidal or conical in shape? Why they're always spherical? The reason is that that's the most stable shape, and stability is always measured in terms of energy. So everybody, everything, everywhere, even us, always want to reach a very stable state, and that stable state is always achieved when we are at our least possible energy. Okay, so these masses, when they are constructed and when they are infinite distance apart, will definitely exert an attractive force between each other, and due to that attractive force they'll come closer to each other, come closer, closer, closer. But the next question is, why they're coming closer? Because obviously that's their stable state. They want to reach that state. That's the stable state, right? So they have reached a distance r. Now obviously if we have considered that when they are at infinity, the potential energy existing between both the masses is equal to 0. So obviously when they come close to each other, the potential energy should definitely decrease, right? And that in turn can be justified by the fact that yes, potential energy is decreasing. That means that both the masses are coming in a state wherein they are getting more stable. And this is the relation, this is the reason why they have a negative potential energy right now. Because if it was considered to be 0, because they go potential energy without considering a reference point, you cannot justify a point where potential energy, you cannot give the relation of potential energy at a point at a distance r unless you have justified or specified a reference point. So we have considered a reference point when both the masses were at infinity, हमने 0 consider किया, but now as they are r distance apart, जब वो r distance दूरी पर आ चुके हैं, so now उनकी potential energy पहले से कम होगी, and that too वो negative होगी. कम कैसे हो सकती है 0 से? Negative होके. So there is the negative relation. So keep this in mind with this concept. इस तरीके से आप समझो, you will definitely keep this relation for every, मतलब for the rest part of your preparation कि कैसे होती है potential energy and how it is equal to minus gm1m2 by r. Now let's move ahead. एक चीज और very important, we have considered that when they were at infinite distance apart, potential energy was equal to 0, and this is very important. कल को हो सकता है in advance you can expect a question that this r2 is not considered, मतलब हमने infinity पे 0 ना मान के हमने उसे कुछ और मान लिया. So in that case this will be the relation. Just remember this, ये relation इस तरीके से आई. You already know the force, you just have to integrate it. You obviously know this, right? du is equal to minus of fc dot dr. We have studied this in work per energy. So gravitational force is a conservative force, you just have to integrate it. You'll get this result. You can actually devise this result on your own only. Okay, now let's move ahead and talk about gravitational potential energy. So at Earth's surface, obviously it will be Gme small m upon Re at a height h. You just have to replace this Re by Re plus h. If a body of mass m is raised to a height h from the surface of Earth, what he has done over here, he has done nothing. What he has done is, he has done just replaced this r square and r square multiplied over here. So this Gme upon r square is what? It is what? It is mg, okay, right? And this m, so it will be mg into r square divided by Re plus h. Obviously this won't be r square, it will be r plus h square. Okay, so this Re plus h square over here, it gets cancelled, and finally you get this result, right? Okay, and 1 plus h upon Re, how it arised? Just wait for a while. Dekho, if a body of mass m is raised to a height h from the surface of Earth, so at height h, this is the relation. Now what we need to do, we need to multiply r square and r square over here. So this will instead be equal to g, obviously g, and okay, this is the difference here. This is the difference they are talking about. This is the difference between these 2 points at Earth's surface and at h. Okay, I have got confused it with the potential energy at height h. So this is the difference between these 2 points, and the final relation is this. So at h, at the surface of Earth, when I am moving at a point h, so this is the difference. You just need to keep this in mind, and this relation obviously you can find it yourself. If h is very less than Re, then obviously delta U is equal to mgh, and which we have been extensively using while solving work per energy. We consider the delta U to be equal to mgh, right? And this can be determined using this result, but the result is valid only when h is very less than Re. So obviously all the cases we considered in work per energy were of the pattern that h has been considered very lesser than Re. Means that h can be equal to 100, 200 meter, 1 kilometers also. Okay? It's not a case, because Re is obviously 6400 kilometers. So a small amount of meters will never create a change. Now let's talk about gravitational potential then. It's pretty simple. It's delta U by m. Okay. So gravitational potential turns out to be V is equal to minus G by m. Now while talking about gravitational potential energy and gravitational potential, always keep in mind there's a negative sign. Always keep in mind there's always a negative sign, and you need to remember that. But while talking about force and gravitational field intensity, there that negative sign arises on whichever direction vector you have chosen to be positive and whichever is negative, because they both are vector quantities, right? They have a direction associated with it, but these quantities are scalars, so the negative sign has to be predefined. That cannot change depending on which direction or which consideration you have taken of positive or negative. They always have to be negative, and they are justified. The negative sign is justified by the fact that the stable and unstable regions have existed, and that I have clearly told you. Okay, so always keep in mind the gravitational potential and gravitational potential energy, we always consider it to be negative. There's a negative sign always before that, which is not the case when we are talking about electrostats. Okay, so this thing is important. These differences you need to be very clearly these things should be noted in your mind very clearly when because sometimes what happens, creating similarity and we consider the same relation, we'll write V is equal to Gm by R and the answer turns out to be the other one, and the examiner is so smart that he'll instead be checking on this scale only, whether are you confusing between plus or minus sign. So there will definitely be an option while considering V is equal to Gm by R, and there will obviously be an option while considering V is equal to minus Gm by R, and there develops your potential to do a silly mistake. So now let's talk about gravitational field intensity. And what is gravitational field intensity? The relation is same as of electrostats. It will be electrostatic force divided by the mass m. The mass m on which that gravitational force is being exerted. So here is mass capital M, here is mass small m, and suppose because of this capital M, this small m is experiencing a force, and that obviously will be equal to G capital M small m upon R square, right? Yes, right, sir. So this F by this M will instead give you G capital M by R square. Now which direction I have specified the R vector? So if this is positive, then obviously R vector is this. Okay, this is positive, right? R cap, the intensity is obviously along the force. So if this is the R vector, this will be positive. Okay, so this was all about gravitational field intensity. Now what we are going to start now is about the gravitational field and potential for different bodies, for spherical shell, for closed sphere, for different bodies. So we'll be discussing about them, but I'll be needing a break and I'll be going and coming very back soon. Okay, so till then आप इन चीज़ों को revise करो. I'll be back in a moment. Okay, bye bye. Okay, so we are back again. I'm audible? Yes. Subscribed, sir. Joel, okay. Hello, hello, hello. Yes, Umesh, what's your doubt? Tell me, Umesh, बताओ आपका doubt क्या है? Now let's solve this question of, it's not a question, it's a basically concept. So gravitational field and potential. So about a ring, if we have 2 points, inner, surface and outer. So what will be the values of gravitational field and gravitational potential at all these points? Let's discuss them. So inside, if I talk about, no, not outside, it's R is greater than capital R. So it's an outside point. Then for outside points, what this does is, this entire ring, since it's symmetrical about its center of mass, can be about its point O. So we can consider this entire mass to be concentrated about its center, and that in that case it turns out to be a point mass of mass capital M. So the gravitational field intensity and potential are pretty simple. It will be equal to Gm by R square and minus G by R. Now if I talk about center, no, not center, if I talk about the surface, that is this point, in that case also we can consider the entire ring to be concentrated about its center, okay, the center of mass. In that case also, the result, only the R value changes and it becomes equal to capital R. Now if I talk about a point inside the ring, then obviously its gravitational field intensity will be equal to 0, and using the same concepts of Gauss law only, if I construct a Gaussian surface, there is no mass inside this, so, and the outer mass is always symmetric, so the gravitational field intensity over here at I will be equal to 0, but the potential will be same as that of the surface. So throughout this figure the potential remains same, and that is equal into what was it at the surface. Now the graphical representation is something like that. Give it a pause and just go through what this graph is all about, because such kind of graph questions are also used and asked very clearly, or very they are asked so many times in exams, so you should just get a sync with them. Yuvraj, good morning. Okay, so for a uniform solid sphere, now let's talk about a uniform solid sphere. So uniform solid sphere with uniform mass distribution, obviously it's uniform, that means its mass has been distributed uniformly. Okay, now same approach, having an inner, outer and surface point. So if I talk about a point outside, then again the case remains same, it gets concentrated about its center, becomes a point mass, and the gravitational field intensity will be Gm by R square and potential will be minus Gm by R. If I talk about the surface, same thing, just replace this small r by capital R. Now if I talk about a point inside, then we need to remember very important two relations, and they are very important indeed. So the gravitational field intensity now will be equal to Gmr upon r cube. What it is? Gmr upon r cube. And if I talk about this relation, potential at any point inside, this is also very important, and this is actually equal to minus Gm by 2r cube 3 capital R square minus small r square. इस चीज को याद कर लो. I want you all to remember it. आप इस relation को हमेशा derive नहीं कर सकते. This relation has actually been derived using this result. Okay, E dot dr is equal to minus is equal to dv. So this is the relation between dv and dv and electric field, potential and electric field. Over here it will be gravitational field intensity, not electric field. See, I also relate things. I also relate the concept of electrostats and gravitational field, and hence is the reason I wrote E over here. But it will be gravitational field intensity. So this is a relation, and using this it has been derived. But I don't want you all to actually remember the calculus part or the derivation part. I want you to clearly remember this formula. It is very important. And if you remember this formula, you can very well find out the value of potential at any point inside. Be it the center, replace small r by 0. Be it the surface, replace small r by capital R. So here goes the relation. At center, it will be equal to 3 by 2 times the surface. So the maximum potential will be at, not the maximum potential, the least potential will be at the central point. Okay, the least value of potential will be at the central point, and as I move away from it, the potential decreases, and at infinity it will be equal to 0. And so here we have the graphs of potential and electric field. For electric field it will be a straight line, then it will be a curved following inverse square law, and over here the pattern will be, initially it will be parabolic, then it will become a hyperbolic curve, but the relation will be somewhat like this. So always remember this. Okay, now if I talk about a ring, and we already have discussed ring, but when the ring was on this 2D plane, okay, when the ring was on its in this 2D plane, this is a 2D plane, right? Now I am considering, suppose the ring is over here, so I am considering a point outside it, over here, somewhere over here, okay. So I have constructed the ring over here and I am considering a point, basically on its axial point, on its axis I need to consider a point at distance x. What is the value of gravitational field intensity and gravitational potential? So this relation also I want you all to remember, because remembering over here or remembering over there in electrostats is the same thing. You just have to replace the gravitational constant with 1 upon 4 pi epsilon naught and the result remains as it is, okay, and obviously q by m. So for electric field part, it will be equal to gmx upon r square plus x square to the power 3 by 2, and the gravitational potential is minus gm upon r square plus x square. Do remember it, mind my words, it becomes very easy in examination when questions based on this are asked. So suppose that the question will be, so here is a ring, I placed a mass m, tell me the amount of force, or it has moved a distance x, tell me the amount of work done. So in that cases you need to remember the gravitational field intensity because of that ring at this point at a distance x, because that will be pretty easy. Now just deriving the result over there will consume a lot amount of your time, that is pretty precious that time. So do remember this result. Again I am stressing upon this one, this relation and this relation. Other relation are very simple ones, so you don't need to stress more upon that. Solving 2 or 3 questions will definitely make that fit in your mind. So remember this. And one more thing, the graph of gravitational field is somewhat like this, okay. The graph of gravitational field is somewhat like this. So what happens is, there occurs a particular point when the gravitational field intensity is at its max value. So it is 0 at the axis, it becomes a maximum value and then it again decreases, and this point is obviously r by root 2. It is obviously r by root 2 and it occurs on both the ends of the ring. So this will be suppose r by root 2, okay, and over here also on the back side of it also there will be a point r by root 2. Obviously it will be minus r by root 2 if you are plotting it on a number line on x axis. So over here and over here the gravitational field intensities are maximum, and the maximum value is, if you just remember this point, you can just replace it over here in this relation and you will get the maximum value of gravitational field intensity also. So do remember the case whenever I talk about a ring on its axis, there occurs 2 points one on the left side, one on the right side, whose value of gravitational field intensity is maximum, okay, and the distance is r by root 2, okay. Now let's move ahead and talk about escape velocity, the very important one, very important escape velocity, what it is. So the basic idea behind escape velocity is, see, when I was a kid I also got confused when I heard this for the first time, that to leave earth we need a speed of 11.2 kilometer per second, but that is not the speed just to leave or to leave the surface of earth or to reach a particular orbit. No, that's not the speed. That is basically the speed that has been provided to, if you just remember Voyager 1, Voyager 2, the 2 spacecraft satellites which have been projected from earth to just leave our sun space, the space of the influence of sun. Okay, so presently they have left, they are in the interstellar space, both Voyager 1 and Voyager 2, which were released somewhere in 1980s by NASA. So they were projected at somewhat of this speed. So this escape velocity, the funda of this escape velocity is that to have an object thrown or projected from the surface of earth such that it leaves the gravitational influence of earth completely. And when can we say that the gravitational influence of earth has ended? So that will obviously be an infinite point, right? And if that infinite point has been reached, then we can say it has left the gravitational influence of earth. So what I mean to say is, the escape velocity is that minimum velocity provided to an object such that it leaves the gravitational influence of that planet from which it has been projected, or else the object reaches an infinite distance from that planet. So at that planet, whether its velocity now becomes 0, that I don't care. So if I talk about the minimum velocity, then obviously when it will reach infinity from that planet, its velocity will become 0. I don't need to impart an extra velocity to it, right, when it reaches an infinite distance. So that's their case. But the minimum velocity for which, the minimum velocity will obviously, when the object reaches infinity, it has a velocity equivalent to 0. And if I provide it more than 11.2 kilometer per second, that is the escape velocity of earth, then obviously when it reaches infinity, it will definitely have an velocity. But this is the sole case when I am talking about a system wherein only earth is located, okay. There is only earth and Earth was only a gravitational influence, so I just need to project an object just to leave the gravitational influence of Earth. But that's not the case in reality, right? We are in a solar system, so Sun has a more influence than Earth. So we need to provide a force and the direction also. We need to provide a direction also, in which direction we should project the satellite or the rocket, so that it gets maximum velocity, and obviously so much amount of mechanics is also involved in it, that one question I asked in the previous webinar which was conducted yesterday, that why all the major space launch stations are equated near the equator. And the reason to this is, if you talk about our Indian space, it's Dhawan, right? Dhawan space station. So if you talk about that, the launch station, or the French Guinea, from where Ariane 5 carrier is always projected, so that is also located just above Southern America, if you just locate it on a map. So what I actually, or if you talk about the NASA space launch station as well, that is also located very near to equator. And the reason to all these things are that as we are near to the equator, we are at a greater tangential velocity, that you can very well know. We all are moving at a constant angular velocity, right? For us, for each and every one of us, the day ends in 24 hours. So all have a constant angular velocity, but the tangential velocity obviously varies. So as we move away from the axis, the tangential velocity will be more, and this is the reason why major launch stations are located near the equator, just to provide them with an extra velocity because of the tangential velocity on Earth. Okay, so this is the reason why major launch stations are located near the equator. Okay, so along with this, we use this elliptical path also, that when it reaches a very close point, its velocity is more. So such kind of a thing was also used in the projection of Mangalyaan. So many things are actually involved while projecting a satellite or throwing anything in space to reach a perfect destination. So these are very interesting concepts here. We'll be creating so many content regarding this, don't worry. But for the time being, let's just focus towards escape velocity. So what it is, I just told you the information, I told you the definition. We just need to leave the gravitational influence of Earth. So how it will be, I'll be using work energy theorem. So delta K plus delta U will be equal to 0. Now what I want is that the object should be thrown away from Earth, it should be projected from Earth such that it reaches infinity and its final velocity becomes 0. That is the minimum velocity, right? So finally its velocity should become 0, and initially should be equal to half m v square. Okay, perfectly fine. And now what about change in potential energy? So right now on Earth it has a potential energy, but when it reaches infinity, the potential energy will be 0, because obviously I have defined potential energy when I have considered that at infinite location the potential energy is equal to 0. So finally my potential energy will be equal to 0, and initially it will be equal to minus g capital M small m upon r, that is radius of Earth. And this is the case, and just equate it with 0 because no other forces are acting on the system. Okay, no external force, no non-conservative forces are acting. We are obviously negating the effects of Earth's atmosphere as well. Okay, so many considerations have been taken, but it is just to make you understand this very simple concept of escape velocity. So over here, just equate it. This is the relation which is given over here. So you can just find the value of VE, and it is instead turning out to be 2 times GME upon RE. And if I talk about any other planet, just replace this mass and radius of that planet over here. So you'll get the escape velocity from that planet. Okay, so this is the relation. Keep this in mind. This can also be written as just multiply R and R over here. So GM upon R square will be equal to G. So it will be 2GRE. Okay, so at Earth's surface, on replacing these values, 6400 km over here, G as 9.8, you'll get that this velocity is turning out to be 11.2 km per second. So if an object is projected, if there is a system only of Earth, no other planet is in influence, no other planet is actually creating a disturbance. So if a planet Earth is only existing and we need to just throw the object such that it reaches an infinite point, the minimum velocity should be 11.2 km per second. I suppose you got it. But if we need to place the object in one of the orbits, then should the velocity should be 11.2 km per second? No, not at all. Not at all. We don't need to impart this much amount of velocity. We just need to place it in an orbit, right? So giving that velocity will never ever make it form in an orbit. For an orbit, a specified defined velocity is made given to the satellite such that it performs a circular orbit or an elliptical orbit around any planet around us, obviously around our Earth. So for that we need to focus now on orbital velocity, but moving forward for that we first need to solve this question. So what it says is the satellite is revolving in a circular orbit at height h from the Earth's surface. Perfectly fine. The minimum increase in its orbital velocity required so that the satellite could escape from the Earth's gravitational field is close to. So I'll be solving this question, but first let me tell you about orbital speed only. Let's discuss about orbital speed. So what it is? So whenever an object has to orbit Earth, suppose an object and a satellite is orbiting Earth, right? And it is orbiting Earth around a circular orbit, obviously. So is something hitting in your mind? आपके दिमाग में एक घंटी बज रही है कि ये सर्कुलर ऑर्बिट में मूव कर रहा है तो एक फोर्स टुवर्ड्स सेंटर होना चाहिए. देयर शुड बी अ फोर्स टुवर्ड्स द सेंटर, राइट? And yes, there will be obviously, and that will be gravitational force. So this gravitational force only will be providing the necessary centripetal force. Yes, obviously, sir. So if it is providing the necessary centripetal force, then I can equate it with G capital M small m upon r square, not r square, it will be small r square, wherein small r is what? Small r is this distance, this from the center of Earth, this distance will be equal to mv square by r, right? Obviously. So and this will what? This will be the orbital speed. The tangential speed with which it is moving in that circular orbit. Just remove this r from here, m from here. What you'll get is VO is equal to under root of gm by r. So if this r is very close to the surface of Earth, this r will get replaced by gm upon re. And if you look closely over here, escape velocity from the surface of Earth is 2 times gm upon re. So orbital speed and escape velocity have a relation in them. Okay. So if I talk about a distance r, suppose I am not interested in escape velocity from the surface of Earth, I am interested in escape velocity from this distance. What will be the escape velocity from this distance? So I just need to replace this radius of Earth over here with r. So over here it will be v will be equal to 2 times gm upon small r, and the orbital speed over there is under root of gm upon r. And as you can notice, escape velocity will obviously be root 2 times orbital velocity, and this is the relation we need to keep in mind. Okay, so at any point we are situated, our satellite is situated, the orbital speed over there will be under root of gm by r, where r is obviously the distance where we are situated from the center of Earth, and the escape velocity will be under root of 2 times gm upon r, where r is obviously the distance from where we are located with the center of Earth. Okay, now let's solve this question then. So this question says the satellite is revolving in a circular orbit at a height h from the Earth's surface. Okay, no problem. H is very less than r. That's also not an issue. So we can just omit this h and we can consider that we are situated on Earth only. The minimum increase in its orbital velocity required so that the satellite could escape from the Earth's gravitational field is close to. So what this says is, here is Earth and a satellite is rotating very close to the surface of Earth. Okay, very close to the surface of Earth. This h is not that much. It can be 1, 2, 4, 5, 10 kilometers. So it's not that much amount. So we can consider the distance of that satellite to be re only. So what will be its orbital speed? Orbital speed will obviously be under root of gm upon re. Okay sir, no problem. What we need to find? We need to find the minimum increase in its orbital velocity. कितनी देनी है? ठीक है. And what about its escape velocity? अब मुझे escape कराना है. I need to make sure that this satellite over here should escape the Earth's gravitational pull. So I need to provide it with an escape velocity. And what should be the escape velocity? It should obviously be equal to 2 times gm upon re. So here it has this velocity. I need to provide him with this velocity to the minimum increase. How much it should be? How much it would be? It should be v minus vo. So v minus vo will obviously be equal to root 2 minus 1 under root of gm upon re, and this gm upon re can be represented as vo. So it will be equal to obviously root 2 minus 1 times vo. And is this the answer? Yes, it is. This gm upon re, I can just multiply this re over here and re over here. This will instead turn out to be small g, so it will turn out to be under root of gr, and this is our correct answer. I suppose you have understood this question. It was a very simple one. You just need to understand the basic concept of whatever be your position. There, if you are rotating, if you are revolving around Earth, then your orbital speed will be under root of gm upon r, and if you need to escape from that particular place, then your escape velocity should be under root of 2 gm by r. Okay. So now let's move ahead and talk about the very famous Kepler's law. Okay, so these Kepler's law actually were Finally, very helpful in understanding how gravitation is actually working. Okay, what are its three laws and how they helped us in understanding the planetary motions. Okay, how planets are revolving around sun, and they were very useful. So the first law was about law of orbits, and he told that the planets around sun, they are not making circular orbits, they are instead revolving around the sun in elliptical orbits with sun at one of its foci. So an ellipse, obviously an ellipse is a compressed circle, right? So it has two foci, one is over here and one is over here. Okay, one lies over here and one lies over here. So at any of the foci, a sun will be situated, and this planet will then be revolving around the sun in elliptical path. Okay, so obviously there will be a perigee point when sun is closest to it, there will be an apogee point where earth is at the farthest point to it. Okay, some more important elements. So the position of the apogee will obviously be this RA distance from here to here, and the perigee will be this RP distance. In a ellipse, this distance is known as semi-major axis, and it is equal to 2a. Okay, 2a. And what will now be the distance between this perigee, this AP, RP, how much it will be equal to? So this RP will be, if I calculate this distance, this is the semi-major axis, it is equal to a. And this distance from the center point to one of its foci is equal to a times E. And E is what? E is the eccentricity. E is what? E is the eccentricity of this ellipse. So this will be equal to A minus AE. Okay, and if I talk about the apogee point, that is the farthest point, it will be equal to A plus A. As you can see, A plus A. Okay, this distance is A. This distance is A from center to where the focus is located. So this will be the value of RP, and this will be the value of RA. I suppose you are getting it, that the distance, the position of the perigee point की दूरी कितनी होती है? A minus AE, and apogee point की जो दूरी या distance होता है, that is equal to A plus AE. Okay. So this was all about law of orbits. Now let's move ahead and talk about law of area. And the law of area actually gives us a very important relation about conservation of angular momentum as well. So conservation of angular momentum can be found out using this law as well, or using our law as well of rotational motion, wherein we told that yes, the torque about sun will always be zero. Reason is that there is only one force acting on a planet when it is moving in an orbit around sun, and that is gravitational force. And since it is passing through the axis of rotation, that is sun, so hence we can conclude that the torque about that only force will be equal to 0, and if net torque acting on a system is 0, then its angular momentum remains conserved. So this was pretty clear previously as well. Okay, now the law of area states that the planetary motion, the motion of a planet, it sweeps equal area in equal amount of time. Now how we are calculating area? So the position vector basically between the sun and the planet. So here is sun, here is planet. So this position vector which you are seeing, this direction, it sweeps an area. It sweeps an area. So it sweeps an area equally in equal amount of time. So in delta t time it will sweep this much area. And as it moves closer and closer, so suppose if I take the reference of 1 day, so 365 days, 1/4 days it takes, right? So here is earth, here is earth, here is earth, and here is sun. So suppose now for 1 day it has swept this much area. For one another day this has sweep this much area, and when it is closed over here it will sweep this much area. Okay, let's take the case of 1 week. So 1 week it swept this much area, because obviously it has to be very constant with the area. So in 1 week it will sweep this much area, and in the next week over here it sweeps this much area. And how come it is happening? Because angular momentum is conserved. When it reaches this point, its velocity increases drastically. Its velocity increases drastically, and it reaches the apogee point, its velocity reduces. And this concept of elliptical motion is used very wisely. Very wisely, I'll tell you how. So from here we can finally conclude that since dA by dt is equal to L by 2m, and second law says that it is equal to constant, and obviously mass is not changing, the mass of a planet is not changing, so this 2m will get over here. So finally what we can conclude is that angular momentum is constant. Angular momentum is constant. Okay, and if angular momentum is constant, then what we can finally derive is, I'll just tell you in a moment, just first let's discuss about this third law as well, law of periods, and it just says the periodic motion of a planet around the sun, the time period, the square of it will be directly proportional to the cube of the semi-major axis. I am again repeating myself, the square of the time period of planetary motion will directly be proportional to the cube of the semi-major axis. Okay, so these are the three laws. Now let me tell you about elliptical path. So suppose here is an elliptical path and it says that angular momentum is conserved, right? So if angular momentum is conserved, that means the angular momentum at this perigee point, so LP it will be m Vp into Rp, and over here at apogee point will be m Va into Ra. So as you can see over here, at this point, suppose it is moving like this. Okay, so it will have a velocity over here and it will have a velocity over here. So since this distance is very much, as compared to this distance, so over here the velocity should be more as compared to this point. So whenever a planet or any satellite moving around Earth even, whenever it reaches the perigee point, its velocity becomes very large, and this kind of a concept has been used very widely whenever we are about to project any satellite or any like the recent case of Chandrayaan, right? So in Chandrayaan what happened was ki the satellite was made to move in an elliptical path, then again the rocket was boosted and its velocity increased and it again came over here with an increased amount of velocity. So whenever it reached this point, the booster shot was given and this path was again increased. Okay, so on increasing the velocity over here, what happens? The equal amount of radius, the apogee point increases, and with the final shot it just left the surface and reached moon. And such kind of a concept was also used while projecting Mangalyaan. Okay, and so many other things whenever we are about to project so many satellites or probes over there in outer space, we use this concept. Whenever an object reaches its perigee point, we impart a particular boost to it, its velocity increases and in turn its path also increases. The apogee point distance increases and finally it can leave the gravitational influence of Earth on reaching a particular distance. Okay, so this was all about Kepler's law. I suppose you have got this entire ideation. Now let's move ahead and talk about orbital speed, and we have already discussed about orbital speed. So suppose Earth is there and a particular satellite is moving around it at a distance r. So the only force acting on it, that is the gravitational force, will provide the necessary centripetal force, and in such a manner we can obviously find the value of orbital speed, and that is equal to gm upon r. Now suppose it is situated at an altitude h from the surface of Earth. So this r can be replaced by re plus h, because the distance, the reference point of all the distance is always understood with the reference of center of the Earth. हम center of the Earth के reference में ही कोई भी distance define करते हैं. So this small r will be equal to re plus h. Okay. Now if re is very greater than h, that means h is near about 1-2 kilometers or 3-4-5 kilometers, then this h is obviously very small. 6400 plus 5 kilometers. So suppose I have given you 7000 rupees and I am giving you 5 rupees more. So you will just consider me, sir, what are you doing? We don't need your 5 rupees help even. You have 6400 rupees, man. So this h can be omitted obviously, and this relation will finally turn out to be gm upon re, and this is instead escape velocity upon root 2, because the relation of escape velocity was under root of 2 gm upon re. Okay, so the relation turns out to be like this. I suppose you have understood. Curved at corners and slightly plane at poles is elliptical like a compressed sphere. Obviously you are right, you are absolutely right. Okay, now let's move ahead. Okay, Edu was asking what's elliptical. Elliptical is the motion on an ellipse. That's an elliptical path. What is circular then? The motion of a path in a circle. So circular, elliptical. Okay, now let's talk about per time period. How to calculate the time period of a satellite. So what you need to do over here, what you have used this formula, right? So instead of this formula, just use this formula, m omega square r. What you need to use, just equate this m v square by r for calculating the orbital speed. Now just equate it with m omega square, and what you will be getting is the angular velocity, and angular velocity is obviously 2 pi upon t. So on replacing omega by 2 pi upon t, you can very well find out the value of t. Pretty simple. So this is the relation of t, right? Just do it yourself and just find this relation. Okay. Now for a satellite orbiting close to the surface of Earth, obviously if this r is very small, this relation can obviously be turned out to be it can be written as 2 pi under root of r e cube. So I will write as r e square into r e upon gm, and obviously gm upon r e square is what? G. So this will turn out to be r e upon g, and it will turn out to be 84.6 minutes. So in a span of just 84.6 minutes, a satellite will orbit around Earth if its height is very close to the surface of Earth. Just imagine the speed. Just imagine the speed of that satellite, which is instead orbiting around Earth in a span of just 84.6 minutes. Okay. Now let's talk about, if you are talking about satellite motion, then we need to talk about the energy quotient as well. So when a satellite is moving, obviously it is in motion, so it will possess a kinetic energy, and that will instead be equal to half m v naught square. It will be equal to what? Half m orbital speed square, and orbital speed is what? G capital M upon r, G capital M upon r. So it turns out to be this, right? So this will be the kinetic energy. Obviously it is in plus. Now it is also there also will be some potential energy, right, between the satellite and Earth system. So here is Earth, here is the satellite. Okay, here is the satellite. So there will be a potential energy between both of them. That will be equal to minus g small m capital M upon r, where r is this distance. Yes sir, definitely. Now, so the total mechanical energy will be just the addition of this, and it turns out to be this. But this relation, don't consider it to be pretty simple, because there is a negative sign over here, and this negative sign is very important. This actually tells you whether this satellite, there's also a way to judge whether a satellite will be able to maintain a bounded path around Earth or not. If its total mechanical energy, if it is always negative, then that satellite will never ever leave the influence or this circular orbit around Earth. If it becomes 0, then it can leave it. If it becomes positive, then it will surely leave. But till the time it is negative, the total mechanical energy of two systems are negative, they will definitely be in a bound system. So always remember that this negative sign over here suggests that this satellite Earth system is a bound system. That means the satellite is bound to Earth. It will always revolve around the Earth. Okay. So here is the relation. I suppose you have understood it. Now let's talk about geostationary satellites. Very important one. Very, very important. Sir, what is the formula like? Sat of 8 by 3 pi g r square of escape velocity. Wherein escape velocity? This one. Here you have just replaced m by rho. Rho is what? Uniform mass density. Just replace it with rho. Rho is what? Capital M upon 4 by 3 pi r cube. You'll get this relation. Okay. Now let's move ahead and talk about geostationary satellites. Very important one. Why very important one? Because the entire communication, see, suppose I am conducting a lecture over here and this session is live for you people, right? So how come this live session is conducting between us, and how communication, satellite phones are working, or how me over here can talk to someone over situated there in US, that distance apart. So these communications, how they are occurring, obviously you all know they are occurring through antennas which are transmitting the satellite, and then satellite is again transmitting to the receiver, and the receiver then proceeds with the demodulation part, and finally the signal is created, the signal is goes to the receiver. But suppose that satellite is not in a rigid state, right? It's not in a fixed state. The Earth is in rotation and so is that satellite. So how come that antenna which is situated upstairs on a building knows the perfect location of that satellite? Because the location of that satellite is instead fixed with reference to us. And how is that possible? That is obviously possible because we rotate in a span of 24 hours, right? We rotate in a span of 24 hours, and the revolution of that satellite is also in a span of 24 hours only. So if r omega, whatever be r omega, and that is the omega of that satellite also, if they are same, so from our frame the satellite will always be situated just above us, right? So there is the satellite and that will be the position. So as we are rotating, it is also rotating. So basically the revolution period of that satellite is 24 hours, equivalent to the rotation period of our Earth. and this is the reason the satellite is always situated at a particular location. Okay, and this is used in communications. Okay, so whenever we are about to communicate things, satellite phones and all these stuffs are done using geostationary satellites, but projecting a geostationary satellite is not that easy even. India now are amongst a group of countries which has successfully done its testing, and they are actually projecting satellites through their in the geosynchronous orbit, not the geostationary orbits, in the geosynchronous orbits through our launch vehicles. We have successfully done that. So India is among the elite countries. There are top 5 to 4 countries which are able to project these geostationary satellites. Okay, and launching a geostationary satellite, obviously you can see the height. The height is obviously 36,000 kilometers from the surface of Earth. That's a very huge amount. So at this distance, a geostationary satellite is positioned above the surface of Earth. Then only it will have a revolution period equivalent to 24 hours. And getting a satellite till this level requires huge amount of energy. Basically, cryogenic engines are required to project a satellite at this much height. So it's a very tough thing to do, but we are now a new entrant into that. Okay, so this is all about geostationary satellite, that at 36,000 height from the surface of Earth we position a satellite, and at that point the revolution period is equivalent to 24 hours, and those satellites are used for communication purpose. There are some other satellites as well, known as polar satellites, and India is an expert in launching polar satellites using our PSLV. Polar satellite launch vehicle. So what they does is they help in geomapping. Okay, the geomapping one, the map or the winds, the rains, whatever climatic change will occur, or to solve any such problems for the army, for the naval, for the defense services, what all things occur, they are done using those satellites. Those are polar satellites known as, and India is an expert in that. Okay, but here we are talking about geostationary satellite. Let's look at some points over here. So the plane of the orbit is always equatorial plane. In the equatorial plane only they are launched. Okay, at 36,000 kilometers, as I told you, known as the parking orbit, where the position of the satellite is placed. Orbital speed is nearly 3 kilometer per second. Just imagine. The orbital speed is nearly 3 km per second, and the time period is obviously equal to 24 hours, as has to be the position, it has to be same. The orbital radius is nearly 4,400 kilometers, and obviously this is measured from the center of Earth. So just add 6,400 km to it, you will get the result as 42,400 kilometers. Their orbit contains axis of rotation of the Earth. Obviously along the axis of rotation of Earth only it has to use. They are used for remote sensing. So you got the idea. What is the ideation behind geostationary satellites? Now let's move ahead and solve this question. Okay. A satellite revolves in the direction of Earth's rotation, that is from west to east. So we obviously also rotate from west to east, and this is we rotate from west to east, and this is west to east, and this is the reason sun appears from east to west. Okay. Sun is not revolving around us. We are rotating from west to east, and this is the reason sun appears from east and sets in west. So the direction in which we are in rotation, the satellite is also revolving in the equatorial plane. For an observer on Earth, time interval between its two consecutive appearances overhead will be. Okay, no problem. Pretty simple question. Let's solve it. So what happens is, suppose here is Earth and we are situated over here, and here is the satellite. So we are in rotation with angular velocity of WE. Okay, and obviously this satellite is also in revolution around us, and it has an angular velocity omega p, as has been mentioned. So from my frame of reference, what will be its net angular velocity? There can be a case that I have a more angular rotation period, so the net will definitely be equal to, if omega e, that is the angular rotation, the angular velocity of Earth is greater than the angular velocity of the satellite. This is the satellite. So then in that case, the angular velocity of satellite from my frame, that is from Earth, will be obviously equal to omega e minus omega s. Okay, so since I am moving in such a direction, I will it will make it feel that it is moving in opposite direction, right? But if omega e is lesser than, lesser than the satellite's angular velocity, then obviously the satellite's angular velocity will be equal to omega s minus omega e. Just the case which you have studied in relative motion of one dimension or two dimension, that from my frame of reference, I am also rotating, the satellite is also rotating. If I am rotating at a faster pace, the satellite will appear to move anti-clockwise, the opposite direction to my rotation. But if it is moving at a faster pace, then it will appear to me moving like this. So the net angular velocity observed by me will obviously be equal to omega s minus omega e or omega e minus omega s, depending upon whichever is higher. So with this angular velocity, how much time it will take to appear twice? Once it has appeared to me, right now it has appeared to me. Now after how much time it will appear? It will be one circular motion, right? So 2 pi upon whatever its angular velocity. So the answer will obviously be 2 pi upon its net angular velocity, and its net angular velocity obviously will be omega s minus omega e. Okay, if omega e is greater than omega e minus omega s. So I suppose you have understood this question, that how to solve when the satellite will appear again to me. Okay, so now let's solve this another very beautiful question, and we'll be using Gauss law concept over here. So a very long cylindrical galaxy. So galaxy is there, and it is in the form of a form of cylinder, is made of uniformly distributed masses and has a radius capital R, and obviously capital R is very less than small l. A star outside the galaxy is orbiting the galaxy about an axis passing through its center. If the time period of the star is t and its distance from the galaxy's axis is r, then. So here is our galaxy, here is the galaxy, there are so many point masses. Point masses means there are so many stars distributed in it. Obviously a galaxy has a huge amount of gases, nebula and so many things distributed. So masses is distributed, and we have considered that the mass distribution is uniform. Okay, and there is a star located over here, right? There's a star located over here, and it is obviously revolving around this galaxy. So what we need to find, the time period of it, the relation between its time period and the distance, this r. So how we are going to proceed? So over here I am going to use the concept of Gauss law, and what I am going to do, I am going to construct a Gauss law like this. So my Gauss law now will be a cylinder only. So here is my cylinder, and since it is symmetric in shape, I'll assume that the gravitational fields because of this cylindrical galaxy will obviously be radially outward, like this. Okay, yes, definitely sir, it will be radially outward. Now the gravitational field intensity because of these radial outward gravitational fields will be like this, and what I need to do, I need to use the concept of Gauss law. So what was the Gauss law statement in electrostatic? It was equal to integration of E dot dA is equal to Q enclosed upon epsilon naught. So over here the relation will now be integration of I dot dA will be equal to 4 pi g into m enclosed. Okay, so there it was, I just told you 1 upon 4 pi epsilon naught is just similar to capital G. So now 1 upon epsilon naught will be similar to 4 pi g. So I have just replaced 4 pi g into m enclosed, right? So what is the m enclosed inside this Gaussian surface? This is the entire mass of this galaxy, right? So I can write it over here, 4 pi g remains as it is, and I into dA. What will be dA? So dA will be what? dA will be the entire curved surface area. The dA will be this entire curved surface area which you are observing. Okay, this entire curved surface area of this cylinder, this will be the dA, and obviously E and dA are making 0 degree between them. The angle between them, it is also outside, and the dA vector is also outside. I'll be talking about that, how dA vector is outside, when I'll be talking stuff in electrostats, and obviously in this moving charges magnetism as well, whenever I talk about motional EMF and all those EMF dA vector. So I'll tell you how to find out the direction of dA vector, but for the time being assume that electric gravitational field is outside and even dA vector is outside, and the angle between them is obviously 0. So this will instead be equal to I dot dA, and I will come out, integration of dA will be the entire value of the curved surface area. So it will be equal to I into, what is the curved surface area? It is equal to 2 pi r L, right? 2 pi r this distance, and L is the length. So this will be equal to 4 pi g into total mass of the galaxy, that is m. So now what is the value of I? So I will turn out to be 4 pi g capital M upon 2 pi RL, right? Yes sir, it's absolutely correct. It's absolutely correct. So this will be the gravitational field intensity at a distance r. So at a distance r over here, the gravitational field intensity because of this entire galaxy will be equal to, I've just written over here, it will be 4 pi gm upon 2 pi rl, 2 pi rl. I can also cancel this by 2, so it will turn out to be 2 gm upon rl. L is what? L is the length. Now, why I have calculated the value of this gravitational field intensity? Because now I'll be able to calculate the force experienced by this star m. So the force experienced by this star m will be equal to m, that is the mass of this star, into gravitational field intensity, that is equal to m 2g capital M upon r into L. And this force will instead provide this galaxy with the necessary centripetal force, right? So this will instead be equal to m omega square r. And why I am writing omega square r? Because now I will be replacing this omega square by 2 pi upon t, and this r is what? This r is small r. Yes, this r is small r. Small r because this is the distance, right? It is orbiting in this orbit of radius r. So this r will come over here, this omega will be replaced by 2 pi upon t. As you can see here, 1 upon t square will be here, and over here 1 upon r square will be there, and all the other terms are obviously constant. So finally what I can conclude is that you got the point, right? I'll just write it again, cancel this and put this m square over here. So this will turn out to be 2 pi upon t whole square. That is what? It is omega square, and this r square comes over here, so it will turn out to be 2g capital M upon r square L. And as you can see, t square will be directly proportional to r square. So what I can finally deduce is t will be directly proportional to r. Okay, so this is the relation, and is this the answer? Yes, it is the correct answer. So the time period of the star, the motion of the star around the galaxy, the cylindrical galaxy, its time period will definitely be proportional to small r, that is the distance from the axis of the galaxy till the star. So this will be the final question for this session, and I hope you all liked this session, you loved it, and if you like it, you love it, if you got anything which was fruitful for your existing preparation, do give us a like. Okay, we need those thumbs up, and also subscribe to this channel if you haven't subscribed yet. If you haven't pressed the bell icon, do press it for regular updates. There are so many new and good things already on their way. They are about to be published within the coming months. Okay, so it's better if you are well aware of them beforehand. And as I have told you earlier also, in the description you can find the link to our app. Just download it. It is on both the platforms. It has a very rich collection of very good questions which are specially curated by expert faculties over here who already know how to clear this exam. They already have cleared this exam with such good ranks, and they are experienced in their sense, I cannot tell you. So do practice these questions. Also practice these tests as well. Without practicing tests, it becomes very difficult to get that particular confidence which can actually help you clear that particular exam. So your entire strategy should be to learn from these sessions, practice these questions, and give the test accordingly. Okay, plan your time here accordingly. Give some time for basically dekho, the learning part is for 2 hours daily, right? 2 hours at 5 p.m. and on Saturdays it is in the morning from 11 to 1, and then after that plan accordingly कि मुझे इस chapter के questions करने हैं, how I am going to do it. Then after that questions practice करने के बाद give a dedicated time for solving questions as well. If I give a specific dedicated time for practicing tests as well. If I tell you about myself, so मेरा भी approach यही था, but there was no one to tell me, but I figured it out myself, and I was very lucky to figure it out within that time only, not after my 12th got closed, during my 12th class only. So I used to practice a question too much earlier, but thereafter I joined test series and I practiced test series. I practice questions from that, and what happens is giving test also enhances your skills, because giving test and then after that analyzing it also, just analyze your test where you have done the mistake and what is the right approach to solve that answer. That actually increased the level of knowledge which I had, and that was actually helpful in me clearing a rank in JEE, and that was the reason I got selected. So I'll tell you, giving test is very important, and more important than giving test is analyzing it, where you went wrong, how you went wrong, and what was the right approach, and what all silly mistakes which you have the ability to do while in your exam. Those things also will be known over here while giving tests. So they are very important. There occur so many times, yeah. Even I had that not skill but a problem of doing so many silly mistakes, plus minus this into multiplication, these silly mistakes. I know the answer but I wasn't able to do that, but that got reduced only when I solved around 100-200 papers. Then only I was in a state when those silly mistakes are reduced to just nothing. There will be one or two silly mistakes, but that is not a big deal, that can be evaded off. But having so many silly mistakes that your 10 to 15 questions are wrong, even if you knowing the answers perfectly, then that actually is not a good thing. It will definitely decrease your rank, even it can make you not getting a rank as well. So practice question, give test. So when is our next session? Our next session will be on 25th January 5 p.m. Okay, and the topic will be mechanical properties of solids and liquids. Very interesting chapter about fluid dynamics we'll be studying, and it is also very relatable. So do attend this session. Kindly share this session to all of your friends who are in need, and we'll be meeting in the next lecture. Till then, bye bye, happy learning, all the best.